Okay, so welcome to the second session of the morning, and thanks a lot to the organizers for giving us this opportunity. So it will be a session between Swagata, Shilpi, and myself. So we'll be giving like some ideas about long-lived particles. So I'll be starting off with a very biased take on some of the BSM theories through which one could get long-lived particles. So in no way is this going to be a comprehensive talk, because there are many models through which one can get long-lived particles. So let's get started. So before going to the long-lived particles in beyond the standard model physics, so we must, it's a good way to start about listing down the particles in the standard model which are also long-lived. So for example, we can see that, so the shortest lived particles in the standard model are here, which are really short-lived. For example, the Z boson has a lifetime of a mean lifetime of 10 to the power minus 25 seconds. So these particles, electron and neutrinos, they are stable, like all three neutrinos, these are stable in the standard model. In the standard model, the proton is also stable. So let's take some other particles as examples. So for example, if we take a charged pion, so it decays via the weak interaction, and the dominant decay mode is to charge muon and muon neutrino, and we can calculate its lifetime to be of the order of 10 to the power minus 8 seconds. For a neutron, on the other hand, so unlike the proton, for a neutron, it is quite a long-lived particle. So it decays to a proton, an electron, and an antineutrino. So the mean lifetime of a neutrino is 15 minutes. For a muon, which decays to an electron neutrino, and a muon neutrino, the lifetime is of the order of 2.2 microseconds. So again, the standard model particles can be long-lived if there's an approximate symmetry which makes them stable or kind of stable. So for protons, we have the baryon number conservation, which is a symmetry in the standard model. However, in many other models, like in several gut models, a proton can decay with an extremely large decay lifetime of the order of greater than 10 to the power 34 years. So for electrons and neutrinos that I talked about, these are stable because of lepton number conservation in the standard model, and because there are no other lighter particles than these to which these can decay into. For neutrons, we have energy conservation within the nuclei. So these stable particles, the stableness of these particles has to do a lot with the weakness of the weak couplings, the hierarchies of the scales of new physics, and so on. So when we encounter mass degeneracies in a spectrum, we can also have long-lived particles because the decay rates will be suppressed. So we'll be seeing some such examples later on. Also, there can be some small symmetry breaking parameters which could suppress the decay rates. So now, what makes a particle long-lived? So the lifetime of any particle is given as this. So the DLIPS is the Lorentz invariant phase space, and this is a mother particle X decaying to daughter particles PF. So F stands for final. So depending on the lifetime, we'll be able to say whether this particle is long-lived or not. So a particle can be long-lived if the this matrix element is small. So there could be a small broken symmetry, small coupling values. So there could be small phase space between the mother particle and the decay particles. So there could be a nearly degenerate particle spectrum. And again, as I said, coupling suppressed by the scale of new physics. So Shilpi will be saying more on these. So now, like coming to the BSM long-lived particles, there's a plethora of search topologies. So for example, here I list the most commonly searched ones. For example, there's a heavy stable charged particle. There could be disappearing charged tracks. There could be displaced dijets, displaced vertices, displaced conversion, displaced photon, lepton, and displaced dilepton. So I'll be discussing some of these in some details, but like some of the main discussions, the experimental searches will be discussed more by Swagata and Shilpi. Swagata will focus more on the triggering aspects of this. So many models can give rise to such signatures. For example, we can have the R parity violating supersymmetry. We can have the anomaly mediated supersymmetry breaking. We can have the gauge mediated SUSY, split SUSY, and then with Bishrup sir and others, we worked on this a modification of the CMSSM where we can have a long-lived tau particle where we can have neutrino dark matter. So I have these in the backup. So if we have time, we can discuss these. Then we can have some hidden valley models, dark QEDs, axion-like particles, and more. So this is basically a subset of all the kinds of searches that we can actually have. So all of these searches actually require dedicated algorithms, dedicated modifications, additions to trigger criteria, to search strategies, and so on. So I'll be not discussing about the search strategies in this talk, in this part of the discussion. So coming to the first example, so I'll be talking mostly about examples here. So this is the R parity violating supersymmetry. So most of us know that the R parity is defined as -1 to the power 3 B minus L. So the B minus L in standard model is a symmetry, plus 2s, where S is the spin, B and L are the baryon and the lepton numbers respectively. For standard model particles, through this definition, Rp is +1, and for the super partners, the supersymmetric particles, Rp is -1. So in R parity conserving SOSI, the LSP is stable and a potential dark matter candidate often. In R parity violating SOSI, these kinds of particles, which could have been the LSP in R parity conserving scenarios, could actually decay, and we can have a baryon and or lepton number violation. So this is the super potential of the R parity violating scenario, and these are the L, Q, E, D, and U are the superfields which correspond to the lepton doublet super partner, the quark doublet, the charged lepton singlet, down type quark singlet, and the up type quark singlet. And we have these various couplings, the lambda, lambda prime, and lambda double prime, which are the R parity violating couplings, and these are fully antisymmetric tensors. So one example could be a long-lived neutralino in this case. So a neutralino could decay into a lepton and two quarks. So because of the smallness, so see here that this will be induced by such a coupling. Like for example, this could be induced by this parameter, like lambda prime. So due to the smallness of the lambda prime coupling, the decay width of the neutralino is small, which would lead to a long lifetime. So another example of RPV scenario is where like neutralino can decay into 3 almost massless objects, like 3 quarks here. And a significant fraction of the decay particles can move in the backward direction, given that this neutralino is sluggish or slow moving. So for example, we are used to like particles always moving from in to out. But in this case, we can have scenarios where some of the particles could move in the backward direction. So this was a study done with Shankha, Biplabda, and Rohini from this institute. And then we actually see that like in such kind of a sluggish particle, so the angle between the direction of the mother particle, which is X, which is the long-lived particle, and the daughter particles, a significant fraction of them could be greater than 90 degrees, so which is basically moving in the backward direction. So similarly, we can have another example, GMSB scenario. So in GMSB, the SOSI breaking is mediated through gauge interactions rather than through gravitational interactions. And like the SOSI is broken in the hidden sector, and the breaking effects are transmitted to the visible sector through gauge interactions. So typically, in this case, a gravitino is the LSP, and we can have a long-lived neutralino, for example, can decay into a gravitino and some other particles. So, for example, in this paper by Biplabda, Swagata, and Ritoja, who was a PhD student here, so like this could decay to the Z could decay to jets, and we could have missing transverse energy. So, depending on where the Z actually decays, we would see like either like pointed, this is in the eta phi plane, so we would either see pointed energy depositions of the two jets or elongated ones. So in this case, we have the Z displaced by 200 to 220 centimeters in the detector. So the second class I'm going to come to is the LLPs through portals. So we can have the Higgs portal, the vector portal, the neutrino portal, and the axion portal. So these are the popular ones. And so, for example, taking the Higgs portal as the first example, the LLPs couple predominantly to standard model like Higgs. And most of these kinds of portal interactions are dimension 4 operators. So because of that, these are renormalizable. And these are like very popular ways of looking into long-lived particles through Higgs portals. So because the Higgs could be produced through multiple different production modes, there is much scope for couplings of the Higgs to BSM physics being measured through here. So for example, the striking signatures could be exotic decays of the Higgs to low mass particles, and there could be decays in weak boson fusion topologies, Higgs-Stralsund topologies, and so on. So this is quite an intricate model. So one of the first non-trivial examples is a minimal twin Higgs. So here we have an additional twin Higgs doublet amidst an approximate SU4 symmetric potential. So the standard model like Higgs is basically a pseudo-Goldstone boson of this approximate global symmetry. So there are 7 such Goldstone bosons, of which Higgs, the standard model like Higgs, is one of them. So from this model, actually, we can get twin tops, which actually have twin top Yukawas, which are numerically very close to the standard model top Yukawa by construction. We can have twin weak bosons from the gauged SU2. We can have twin glues, twin bottoms, twin taus, twin neutrinos, and so on. And we can actually see that the branching ratio of the Higgs to twin hadron. So this is the Higgs here, the standard model like Higgs, which mixes with this twin Higgs, which then decays to a pair of twin glues, which actually forms confinement. So this is called the twin confinement, which is a very similar confinement that happens in the standard model. So in the standard model also we have glue balls. So here we have twin glue balls, and we have some kind of bottomoniums or other oniums, and the glue balls actually decays to these standard model like particles. So this don't have to focus too much on this graph. So there are, in this model, there are 4 such categories, 4 such decay modes, 4 such regions to be precise, depending on the masses of the particles. So in some mass regions, for example, this A mass region, the mass of the Higgs is greater than twice of the lightest glue ball, so mh greater than 2 m0, and it's smaller than the lightest bottomonium state. So that's why the glue ball actually decays, the Higgs decays predominantly to pair of 2 glue balls. So now the signatures here is that the twin sector glue balls give rise to displaced decays. So here these are the displaced decays here. So for example, the fermions in this case, and the length scale and the lifetime of these glue balls could be the length scale of the LHC detector. So for a scale equal to 3 times the VEV of the standard model like VEV, the lifetime is expressed in this way. So then coming to the next is, how much time do I have? Okay, sure. So coming to the next example, the Higgs portal. So the Higgs portal to a dark QED. So here is the Lagrangian. So we have the chi here as the Dirac fermion, so which could be a dark matter candidate, which couples to the Higgs via a dimension 5 operator. So here, see here, this is the dimension 5 operator, which is suppressed by a scale lambda, because this is 2 and 3. This is a dimension 5 one, and then we have kinetic terms between this the new gauge boson, and we can also have a mixing term here. So which is the mixing between the standard model F mu nu and the F prime mu nu. So the A prime mu here is the dark photon, and the covariant derivative should be modified by from the standard model one by this extra Ig A mu prime. So if the mixing kappa between the 2 field strength tensors is weak, this dark photon here, which is coming from the radiation of this dark matter, like the dark matter particle, so that would be long-lived, and we could have a mono dark photon channel. And this is the lifetime, which is usually expressed in this case. So this is the lifetime of the dark photon. So typically the dark photon decay length is longer than any existing and proposed detectors at LHC, and the authors in this paper actually say that detectors like Mathusla in non-forward directions could be the place to look for such dark photons. So yeah. So these are basically the constraints given for the various the coupling of the dark matter. So Y chi is basically the coupling of the dark matter. So dark matter Yukawa coupling, and this is the dark matter mass, and these are the various parameters that they had chosen: the mass of the dark photon, the coupling, the alpha decoupling, and the mixing. So, and they see that Mathusla can actually be giving very strong constraints in this region. So, coming to the last example here that I have, which is like before the backup. So, the axion-like particle portal. So, the examples where axion-like particles are coming from exotic top decays. So, we can focus on scenarios where axion-like particles only interact with up-type quarks at the tree level. So this is basically the interaction here, the third term. So we can see that the axion-like particles decaying with, interacting with the up-type quarks, with C being a Hermitian matrix here. So this examples of UV completions could include dark QCD-like sectors with scalar mediators, the Froggatt-Nielsen method, and so on. So in this paper here, what they did is they studied the various branching ratios of these axions, and they saw that an axion mass around 1 GeV or smaller would dominantly decay into pair of U quarks or pair of muons, and the others are for heavier axion masses, and these are basically the second ones are basically for the various branching ratios of the top. So we see here that the productions include a top and an axion, and also we can have a top decaying to an axion along with an up and a charm quark. So it's possible to test exotic top branching ratios below 10 to the power minus 4 for a mass of the axion around 1 GeV. So these are I just tried to illustrate a few examples where novel long-lived particle searches could be looked for. So, so we could have displaced jets, as I discussed in the GMSB scenario. We could have displaced leptons, displaced photons, which I did not discuss, but later on we could go into those. So I would like to summarize this part as LLPs arise in standard model as well. Beyond the standard model scenarios, they arise when matrix element is small, phase space is small, couplings are suppressed by the scale of new physics. In SUSY, in R parity violating scenarios, we can have interesting signatures like displaced vertices, backward moving objects. In GMSBs, one could get non-pointing jets. We could have LLPs via portals, like via hidden valley models, ALP portals, and so on. So I would like to give the mic over to Swagata, unless there are some pressing questions. I can't hear you. Could you please speak up?
Sorry. In your Lagrangian, is it possible to have something like a F prime tilde F kind of term?
F prime tilde F, like, are you talking about this one?
Yeah.
So we have an F prime. So I didn't talk about a CP odd F prime in this case, but are you talking about this term, for example? So we have an F prime and F mixing. So are you talking about an F prime tilde?
Yeah. Why not?
So
I think he is referring to CP violating effect.
Oh yeah. So CP
Dark photon.
exactly.
That term is not vanishing. Because it is dark photon, that term is not vanishing.
Exactly.
So therefore, that may have some fresh implication.
Exactly, yeah. So for sure that is possible. It's just that I'm summarizing the results of this paper here. They did not discuss it, but it's definitely possible to include such a term.
Or even a F prime tilde could give you interesting instant-on configurations.
Right, right.
All right. So thank you very much, Shankha, for introducing the basics and all the theoretical aspects for long-lived particle searches. So in my talk, I will speak on behalf of the CMS collaboration about the unconventional triggers for BSM searches in CMS. And while I will mostly focus on the long-lived particle triggers, there is one trigger that is not specifically targeting the long-lived signatures, but any BSM signature. So I will start with a very brief overview of how CMS trigger system works. So LHC collides protons at a rate of 40 megahertz, and this is such a high rate that all these data cannot be stored. So that is why we need a trigger system. So the first level, so we have a two-tiered trigger system. The first one is a hardware-based trigger, and very simple objects are reconstructed at this level. And at this level, since the time we have to take a decision at this level is very little, so we are able to use coarse granularity of the detector. So not all the readout channels can be used, and only the muon systems and calorimeters can be used. The inner tracker or outer tracker cannot be used in run 3 at this level. In the next level, so level 1 trigger manages to bring down the rate from 40 megahertz to 110 kilohertz approximately, and then it goes to the software based high level trigger, and at this level we manage to use the full granularity of the detector, and all the subsystems including the inner and outer tracker can be used here. What comes out of the high level trigger are 3 things. One is called standard stream. So the events that belong to the standard stream, they are very quickly reconstructed offline, and the full event information, including the raw information, is saved. The next one is called parking stream. Here we do a delayed offline reconstruction because the amount of events stored here is double or more. And the full event information is stored in this case as well. And the third one is called scouting stream. Here the amount of data we are able to store in run 3 is spectacular, but note that there is no offline reconstruction. So the objects that we have reconstructed in the high level trigger, those objects are directly used for physics analysis. So that is why we have reduced event information for scouting stream. So majority of the high level triggers that we have in CMS, they belong to this standard category. And we have about a few hundred HLT paths in CMS in total, and they are used for varied purposes. For example, alignment and calibration of detector components. There are some generic HLT paths which are used in various physics analysis like precision measurement, BSM searches. And then there are some dedicated HLT paths for targeted physics analysis like for LLP searches, and there is some dedicated HLT paths to catch any anomalous event which could be BSM. This is a very new one. This is called anomaly finder. Then parking and scouting triggers also play a major role for LLP searches. The parking strategy, this changes almost yearly according to the physics needs, and currently CMS has a few dedicated parking triggers for LLP searches. And the scouting data has also been useful for LLP searches. For example, we did a search on long-lived dark photon search using muon scouting data, which was published. I do not have time to discuss these 2 streams in my talk due to lack of time, so this will be the focus of my talk. So I will discuss both level 1 and HLT in the context of LLP search and anomaly finding. There are many LLP triggers in CMS. I'll be able to discuss only a few. So the ones that I have chosen are the newest addition to our trigger menu, and some personal bias, and I will only focus on run 3, which is the current ongoing run. I will not speak too much about the past or the future. So to find beyond standard model using the data collected by CMS experiment, we need some triggers. If we knew exactly the signature that we are looking for, we would build a trigger for it. But in the absence of that, what else can we do? So we can make use of modern machine learning techniques, and the ML algorithm will be able to learn how a typical standard model event looks like, and then it will be able to pick events that are not typical. And this is done currently using autoencoder. So we train autoencoder on typical events, which are also called zero bias data in CMS. And then we use the reconstruction loss for autoencoders as a metric for anomalousness. So basically this is how autoencoders look like. Many of you are familiar with it. And if a standard model event comes in here, the autoencoder will be able to reproduce it very well and the reconstruction loss will be small. But if something new comes in, which the model has never seen before, then it will not be able to reconstruct it very well and the reconstruction loss will be high. And by that information, we can trigger on it. So currently, we have two complementary approaches in the level 1 trigger system. One is called anomaly extraction online level 1 trigger algorithm. Here the inputs are PT eta phi of 10 jets, the first 10 highest PT jets, 4 E gamma objects, 4 muons, and the missing transverse momentum of the event. These information are taken from Calo layer 2 and global muon trigger. And the second one, that works on slightly lower level of inputs. So here we use the low level information coming from Calo layer 1 instead of Calo layer 2, and this is using image format. So as you can see that already in run 3, machine learning at level 1 is becoming important, and accordingly the tools have also been developed because we need to implement this in the hardware level or in FPGA. So for neural nets, we have a software, and for boosted decision trees, we have a different software. So this is an example event that was selected by one of these anomaly finder, which was not selected by any other level 1 trigger. So if we did not have this anomaly finder in place, then we would have thrown out this event. And this event looks very interesting. This could be a BSM, this could be just a standard QCD. This is something that has to be checked. So the data taken by such triggers, they are being saved for offline analysis, and that is ongoing, so we cannot say anything right now. So now moving on to displaced jet, just checking how much time I have. Okay, so hadronically decaying LLP is a very viable BSM scenario, as Shankha was also mentioning. We have several displaced jet triggers to capture various detector signatures, and it depends on LLP's lifetime or decay length. So an object can decay to 2 jets, and that decay can happen at various places, and depending on where it is decaying, you will have very different signatures. So just because we have displaced jet doesn't mean that one trigger is enough to capture it. So we have multiple displaced jet triggers depending on where it has decayed. One is tracking based, one is HCal based, and then muon system based. So let's first discuss the first one, which is tracking based, where the decay length is small, which means that LLP, after being produced in the primary vertex, has traveled a little bit of distance, and then it has decayed to jets somewhere in the inner tracker or maybe in the first layer of outer tracker. So this trigger was actually implemented back in run 2, and there was a offline analysis using this data which was published, and this search in run 2, it was sensitive to a large variety of LLP models for masses ranging from 10 GeV to 3 TeV. Now in run 3, the HLT part of this trigger, the high level software based trigger, was improved, and now it is better than the run 2 trigger by a factor of 5 to 10 depending on the mass. The level 1 strategy for this trigger is to cut on HT. So you sum the PT of the jets depending on what is the PT. So HT is a variable that we often use in level 1 and in HLT, also offline. So either it is HT greater than 430 GeV, or if we want to go lower in HT, we can also use soft muons. So triggering on soft muons enables a lower HT threshold and is also sensitive to signatures with B jets in the final state. The HLT strategy is, so in HLT we can run the tracking. So we reconstruct displaced jet with displaced tracks, and we have a prompt track veto. So the early run-through result using 2022 data is already public. So now moving on to ecal based. So here the long-lived particle has decayed somewhere near the outer tracker, maybe very late in the outer tracker, so that the track cannot be reconstructed. So the jets basically go into the ecal and in hcal. So as we know that CMS ecal timing is a very powerful handle for LLP search, and ecal can measure arrival time of objects with a precision of 200 picosecond approximately if the energy deposition is more than 50 GeV. So in this case, the level 1 strategy is to cut on again the variable HT. So HT can be greater than 430 GeV, or if we want to go lower in HT, then we can add a cut on tau PT. Now why tau? Because first of all, if you add the tau level 1 triggers to seed this HLT, we can go lower in HT threshold. And since as LLPs become more massive and more displaced, the resulting jets become collinear and start to look like tau lepton. So even if it is not a tau, it will pass the tau level 1 trigger. So that is what we exploit here. And the HLT strategy is either reconstruct nominal jets, which means that the jets that has some tracks. If it has some tracks reconstructed, it will depend on where it has decayed. So if we can reconstruct tracks, then we reconstruct nominal jets, or if there is absolutely no track and the LLP has decayed after the tracker but before the ecal, then we just have trackless jets, so there is no match track, and then we use ecal timing information for the jet timing. Here there is an experimental challenge that the rates of such HLT pass decay depends on ecal crystal transparency, but that is very well taken care of by experimentalists. And here we just show the efficiency, and you can see that efficiency is higher in this low HT region if we use tau seed. So now moving on to the HCal based one. So here the LLP has traveled beyond ecal and then it has decayed. So there will be no track, there will be nothing in ecal, but there will be some energy deposition in hcal. So this is also a very unique signature. So our hcal has depth segmentation, which means that in this direction, in this outward direction, it has 4 depths in barrel and several depths in end cap. This trigger that I'm talking about is currently focusing on barrel. So, and HCal can also provide the arrival time of a particle. So, these two things, depth segmentation and timing, both of them are excellent for LLP. So, we exploit these capabilities in the level 1 trigger and subsequently also in HLT. So, in level 1, there are 2 scenarios. The objects that are reconstructed in level 1, they can be either time flagged or depth flagged. So, time flagged means that the level 1 system, so the HCal level 1 system, that have detected that the energy deposit that has happened with a time delay. So, that will be the case because if a particle is produced at the primary vertex and goes directly to HCal, it will take this straight path. But if it comes via LLP decay, it will take this long path, and also the velocity with which this LLP travel might be smaller than the velocity of light, because if this is a massive particle, then this will move slower. So if you do the math, there will be some time delay between this and this long path. So that is one way to trigger on it. So what we do is that we use the HCAL time information at the level 1 trigger to identify delayed jets, and this particular example that I am showing is more than 6 nanosecond delay, and we have also vetoed any prompt object. So any prompt energy deposition. And then the depth flag, this means that LLP has decayed after the second layer, let's say, then there will be no energy in the first 2 layers, and there will be substantial energy deposition in the third and fourth layer. So trigger on minimal energy deposit in the first 2 layers and high energy deposit in later layer. That is what it does. And this is just the time flagged trigger. It shows that if the hardware says that the time delay is 8 or 10 nanosecond, then it is time flagged most of the cases. That is what we want. If the hardware is saying that there is no time delay, then it is not time flagged. So it is behaving as we expect. So, and I'm coming to the last one that I want to discuss, which is the muon based displaced jet trigger. So this particular signature is very interesting because the LLP has traveled all the way to our magnet, which is here, and so it has not left any mark in tracker or ECAL or HCAL, and then it has decayed in the muon system. And our muon system has interleaved iron layers, so anything that will decay there, it will shower. So the signature was studied in an offline analysis already in run 2, but they at that time did not have any dedicated trigger strategy. So there were 2 analyses with run 2 data. One is end cap only, the first one of this kind of analysis published in PRL, and then the second one where they also included the barrel and improved the offline trigger strategy, used machine learning techniques. This is currently submitted to PRD. But both these offline analyses used missing transverse momentum as their triggering strategy, which had a bad effect on their discovery potential. So in run 3, the trigger strategy was improved. Currently, it is limited only to end caps. So the level 1 strategy is to count hits in a given muon chamber, and the event will be accepted if the hit multiplicity is greater than some configurable threshold. And here you can see this is a run where the threshold was set to 5, and if the count goes above 5, the event is being accepted. HLT strategy was, so we have some reconstructed hits. So they are clustered using Cambridge-Aachen algorithm, and some selections are applied on the cluster properties. So this is the trigger. Actually, the analysis is currently in progress. So that is also, I just want to mention that the LLP triggering and LLP research in itself is a very interesting thing. So we have to forget our old kind of thinking that jets are seen only in calorimeters and tracker. That's not the case anymore. We can see it also in muon spectrometer. So it depends on the lifetime, and we should try to think outside of the box. Thank you. Urgent questions? Yes.
You said that it will be trained with known samples. So what are those known samples? Like
so there are 2 ways to go about it. One is you can train it with standard model Monte Carlo, but then there is a limited amount of Monte Carlo that you can generate. So we are training with zero bias data. Zero bias data means basically all the bunch crossings that are happening. A part of that we can save, and we can train with that, and the statistics is much higher.
Okay. Thank you.
Okay, so if there is no other urgent question, then I think Shilpi can continue. Okay.
Shankha and Swagata have covered very nicely the theoretical and the trigger aspects of long-lived particles. I'll be covering the experimental aspects of it as to what are the challenges in doing an LLP analysis. So both CMS and Atlas, if you look at the spectrum of LLP searches in CMS and Atlas, you will usually see a plot like this. This has a very varied level of searches, starting from displaced vortices, displaced tracks, displaced jets, displaced muons. The reason why we have so many searches for long-lived particles is because a long-lived particle's time or any given particle's time, it's sampled from an exponential distribution. So depending on its proper lifetime, it can decay substantially in the calorimeters and very less in the muon system, or if the lifetime is proper lifetime is quite large, it can have lesser decays in the calorimeters but more in the muon system. To give an example, so you can see from here that we will have different signatures in the detector depending on the proper lifetime of the LLP. So in both the experiments, we try to cover as much as possible its decays, starting from disappearing tracks, displaced vortices, displaced leptons, multi-track vortices, low EMF jets, and emerging jets and non-pointing photons. And these searches, essentially, they target decays in specific regions of the detector. Some of them target in the tracker, some of them in the muon spectrometer, and some of them in the calorimeters. Now, while the LLP searches are very interesting, but they bring their own challenges with them. So, first of all, reconstruction of objects is usually tuned to detect standard signatures. For example, if you're talking about the electron reconstruction, then it is more idle for its prompt production. Then the second, and I think it's the most important challenge for all the LLP searches, and that's understanding and modeling the backgrounds, because they are not really usually the ones that we see for other standard searches and measurements. The sources could be anything. For example, it could be cosmics, it could be non-collision backgrounds, and it can also be algorithmic sources, as I will give you an example in my slides. And we know history has shown us that it is very important to understand all the sources of the experiment that we are conducting, because we all know the example from the Opera experiment at Gran Sasso. They in 2011 they made they saw a 6 sigma effect that of the neutrinos being traveling faster than the speed of light, and when they reinvestigated where it is coming from, it was coming from this one loose connection which was sending the light signals to the master clock. That was all. So it's very important to understand the sources of our experimental searches. Now, in the next slides, instead of really going into the details or the strategies, I'll mostly focus on understanding the background sources by taking a few examples of the LLP searches. So let me first come to the signatures inside the detector. I'll start with the disappearing track searches. So it has a very distinctive experimental signature. So the kind of signature we will see in the tracker is that we will just see a track that gave hits in many of the layers, but then it suddenly stops. And this could happen, so we'll just see a track like this and maybe some energy deposit in the calorimeter. So this could be because some BSM particle, if its decay products are very low momentum to be detected by a reconstruction algorithm, or the decay products could be very weakly interacting with our detector. Now, in both CMS and Atlas, they have the usual benchmark, signal benchmark that they have taken is MSB, where a chargino decays to a neutralino and a pion, and the mass splitting is very small, so the pion is very low energy, of the order of 100 MeV. So what happens is that the chargino decays to a neutralino and a pion, because pion is very low energy, it just goes undetected by a reconstruction algorithm. So all what we see is just this track stopped somewhere mid in the tracker, recoiling against a jet. So such signatures have a very high PT isolated track, several missing hits in the tracker, in the outer tracker layers, and maybe some small energy deposits in the calorimeter, and huge MET in the system. So the characteristics, now what kind of backgrounds contribute to such searches? This can happen if muon somehow just misses these hits in the tracker, because it decayed in flight, or it produced a heavy EM shower, or electrons if they were directed towards a dead channel in the ecal, and also by taus. Let me just give you an example that if an electron, if it does a very heavy Bremsstrahlung at some point in the tracker, what will happen that it will get diverted a lot from its path, which will not be picked up by the reconstruction algorithm. So what will appear is just some hits here, and then it goes missing. In order to reject these backgrounds, what is done is that we look at the corresponding energy deposit in the tracker, which is very close to the track, meaning if you extrapolate this track to the ecal, you just look at the energy deposit. If it's a huge energy deposit, that would just mean that it's probably coming from an electron that did a heavy Bremsstrahlung. So we reject. That's how we reject these events. Then the other way these backgrounds, this electron could be a background to this, give a signal-like signature, is when this electron hits the calorimeter in a dead region. So it is not reconstructed as an electron, it's just reconstructed as a track with some missing hits. It can have any missing hits. So again, this becomes a background. Then again, give you an example, taus can be fake when when pions from tau decays, they interact with the material of the tracker, and then they give one pion and a proton. So what happens, it again looks like a very just a single track and then some missing hits. So although the probability of this happening is very small, but then the rate of the signal is so low that this can become a huge background for such searches. Now, some algorithmic sources that if we have hits in the tracker, and there could be two possibilities. So in CMS or in Atlas, the way we reconstruct tracks is that we consider all the possibilities of the track reconstruction, and then take the one, choose the one which has the highest quality score. Now, let's say there are two possibilities in which a hit is missing from in the layers in between, and if hits are missing from the outer tracker layers, then this has more chance of getting selected, just because it may have a high Q score. So again, such tracks can become background to these kinds of analysis. Then there can be fake tracks also, that when there are two tracks nearby, let's say, and one of the tracks, in the black lines, you can see these are the real trajectories, but this one has curled up so much that our reconstruction algorithm doesn't pick such kind of tracks. Instead, what it will do, it will just try to align the hits from first track to the hits with the second track. So if it doesn't found tracks in the outer layers, it can also become a huge source. Then selections are just tuned in a way to reject these sources. First of all, there is a huge met in the system, apply isolated track criteria, then require that there are no missing hits in between the tracker layers, because that can be fake tracks, just require outer missing hits in the tracker. So the highest background comes in this analysis comes from the algorithmic error that I just discussed. Remaining is due to fake Lipton. In run 2, a total of 48 events were observed, and they were quite close to what was expected. And here you can see the region that we have excluded from this analysis. Now, a complementary search is the search for heavy charged long-lived particle. So the previous analysis targeted on the decay, the kind of decay, but this one actually is agnostic to the decays of the long-lived particle. It just looks in the energy deposited in the tracker, energy per unit length deposited in the tracker, and there are the analysis have taken these as the interpretations where the gluino could be long-lived because there is R parity conservation, or the chargino has a small phase space as in AMSP, or the couplings between the staus and gravitinos is weak. So what happens is that if these are very heavy charged particles, then they can, if we look at the Bethe block curve, this is very well known curve, they can, and if they are massive, you can see that their beta gamma will fall in the lower side of this curve. What you see on the y-axis is the energy deposited per unit length as a function of beta gamma. So for low values of beta gamma, you can see high energy depositions. So whereas the standard in the particles, as we know in standard model, will mostly lie here in small values of beta gamma in the tracker, these heavy, slowly moving particles will fall in this region. So we expect to see a very high energy depositions in the tracker. So these are actually quite robust searches in the way that they are universal handle for all the charged, slowly moving charged LLPs, and the result is valid for any other LLP model because it really doesn't know anything about how the LLP is decaying in the detector. The major background that comes to this analysis, such kinds of analysis, is mostly when the standard model, so each standard model particle, when it in the tracker, its energy deposition also follows a Landau. So, but we know that Landau has a huge tail. So even a standard model particle, due to fluctuations, statistical fluctuation, it can also deposit huge energy in the tracker. So these very small, rare occurring events become, while they may not be, they are not usually as a background to the usual standard, to the usual searches. These become one of the most important background for this kind of LLP searches. And so I've shown here, taken the results from ATLAS. So what ATLAS does is it measures the energy deposited per unit length in the tracker, and then it maps this dx, energy deposited per unit length in the tracker, with the beta gamma, and then the momentum of the track is known, then it can calculate the mass of that track. And this is what is plotted here. When it plotted here, you can see there is some slight excess in this mass region. And there is an excess of 7 events in this mass range, and the local p-value is around 3.6 sigma, and the global is around 3.3 sigma. So run 3 would be interesting for these kinds of searches. And this, let me also cover this one as well, because I think this is an interesting one. Here we collect events when PP collisions are not there. This is an old search. This has been there since run 1, but I find it very interesting. So this kind of search is designed for those LLPs which have a very long lifetime. So they can decay from several nanoseconds to several weeks. Now, how do we collect them? They won't be reconstructed as in the same event in which PP collision happened. They will be reconstructed as separate events. So how do we collect these events? There's a very nice idea that we know that in LHC, the protons are the proton beam, they are arranged in bunches, and each so you can imagine and then there is a 25 nanosecond gap between bunches, and this big square box is called a train, which is a collection of 25 nanosecond separated bunches. Now there could be a variable gap between two trains. As you can see that there can be a gap of 1 microsecond or 220 nanosecond between these bunches. So the idea is to collect events when these proton-proton collisions are not there, meaning in these gaps. Why? Because let's say if the long-lived particle has stopped in the detector, it will decay at some point of time. So we just try to collect those decays in these periods essentially. Okay, so sorry about the text. So what happens is that such LLPs, they come to stop in the densest part of the detector. This could be calorimeter, electromagnetic calorimeter, hadron calorimeter, or muon chambers. And then they just keep sitting there, and at some point of time they will decay, and we'll try to collect them in those periods. And these are the scenarios considered where a gluino is quite long-lived in split SUSY and decays to gluon and a neutralino, and there are other scenarios. This analysis in CMS essentially targets decays in HCal or in the muon chambers to a pair of muons. So typical backgrounds are essentially when PP collisions are not taking place. So what kind of backgrounds we can expect? Cosmic muons, it's very well known. So cosmic muons are very well known backgrounds to these searches. Then beam halo. So beam halo is essentially the particles which are traveling parallel to the proton-proton beam. They are essentially muons, and they are very heavy, high energy, and they can do a Bremsstrahlung also, very high Bremsstrahlung. So if they do a Bremsstrahlung, they can deposit energy in the calorimeter, and this can look like a jet, or it can give hits in the muon chambers and can look like a muon. So this also becomes an important background to this analysis. Then noise in the HCal also can give rise to signatures for the jet final state. So in order to select for the calorimeter search, meaning for the jet search, to avoid noise, we just require calorimeter based energy to be greater than certain value, much above the noise. Then in addition, we also use how the analog pulse from HCal for a real energy deposited looks like compared to noise. You can see noise is random. So a real energy deposit is, it sharps, it rises sharps, and then it has a slow fall, whereas a noise is random and it's completely different with respect to how a real signal looks like. So we use information from here also. Then to remove the cosmic muons, we can see that cosmic muon is coming from the upper side going towards the lower side. So we use timing information as well, timing information, because here in these muon chambers, we will see that they are arriving early compared to the timing information here. So we just tap on these on these hints to reject the cosmic muon backgrounds. Then for beam halo, if we see aligned hits in these muon chambers, then we say that okay, aligned with some energy deposition, we say this could be a beam halo. Okay, I'll just, so it's a counting experiment. It essentially counts the number of observed events for various signal lifetime hypotheses ranging from 0.1 microsecond to around 12 days. So here I have shown the 2015 and 2016 analysis from CMS because there is no yet the recent one. And here we have excluded gluinos with mass less than 1.4 TeV, and also top quarks with mass less than 744 GeV within this decay, within this proper time. And then there are very recent highlights. This is, I'll just flash in front of you. There have been many interesting results very recently on emerging jets, where they employ machine learning techniques, graph neural networks, and they achieve much better results. And then there are more from recently, just from run 3. I have already put a link there, and they have very much benefited from the latest developments at HLT, as Swagata was also mentioning. So with this, I think the takeaway message is that it's very, for LLP searches, it is very important to understand the backgrounds, because even let's say even 2-3 events, if we see in data, that can indicate a discovery, but we should really first try to understand the backgrounds. Okay. Yeah, thanks.
Questions, discussion points? Wait for a moment.
If I have not missed anything, so maybe all the LLP searches that all of the three of you showed considered one LLP decaying to some visible particles, maybe some jets or something. But can we also include some topologies like one LLP decaying to visible plus LLP, or one LLP decaying to two LLPs that again decay, something like that? Are all different kinds of things also considered?
I would say, if it is allowed by any scenario, I would say it would be interesting to look for it. Let's say if you're saying one LLP decaying to two LLPs further.
Yeah.
So and it depends if the two decayed LLPs, if they can leave signal in the detector or not. If they can leave the signal in the detector, then one can probably try to look at the common point of vertex, and then again two more vertices,
so the
tertiary
reconstruction
vertices.
may be a bit harder there.
But this is, if it is allowed by your model, then I would say it would be interesting.
Thank you.
This is actually a question to all the experimentalists also, because Shankha also in his talk mentioned Mathusla as the place where you could do a lot of these searches. Now CERN, I understand, has a much bigger program of this Howard Physics Facility. What is so great about Mathusla that we always keep on referring to Mathusla as the one where LLP searches should be carried out?
The way I would say, maybe Swagata or Sunananda could add, but it can cover a very highly long-lived particle that will not even decay within the detector, CMS detector. So it can, I have to see what kind of lifetime it can cover.
Yeah, Mathusla is, it is not yet approved, and it probably will not be approved as far as I hear. There are a bunch of dedicated small-scale experiments that are proposed in the context of LHC, and their ideas are the same. There are some free areas in the experimental cavern or in the LHC whole this area, and those free areas can be equipped with some detector material, and we can piggyback on the DAC that is already available for the main detector nearby in most cases. So if we can do this without spending too much money, why don't we do this if it increases our physics reach? That's the main idea.
Swagata, this could be for both heavy charged, heavy stable charged particle as well as neutral particles, and we could it could be forward detectors as well as non-forward ones. So for example, the example that we showed during my presentation is that like this decay of this dark photon would be targeted mostly in the non-forward directions. But then there could be some experiments like MEDAL and others like MOIDAL, which are more forward, right? Like, do you know the status of that?
It's one of the
sorry.
okay. Sorry, I know about phaser. It's already in progress. I mean, there is already the area is identified near Atlas, at least for modal. I don't know. Right. That is right. That is right.
Yeah. So, and I think I just want to add one point. So, like, if you talk about forward facility, so actually you will get sensitive limits if the LLP comes from the decay of, say, hadrons. Okay. But Mathusla is transverse detector and it's not far. So, forward facility is located, say, around a few 100 meters from the IP, Atlas IP. Okay. So, suppose you think about, say, dark Higgs model. So, I think in that case, Mathusla will give you better limits compared to phasor or any forward facility. So, if the mass is, say, above some threshold, like B mass or something, then you have only Mathusla. Phasor will not be very sensitive.
And Mathusla will be for high PT objects as well. I mean, it will go towards a transverse only. So that's why Mathusla is quite important.
How do you know, okay, that Mathusla will never be approved?
Yeah, that
I
is
had
something
a discussion with
Gordon.
Gordon at some point in time, and the thing is, okay, I mean, currently, okay, the Mathusla has a what do you call their estimated budget is too high, so they're saying, okay, if you can cut down the budget a little bit, then I think it will be most likely approved.
So what I heard is that every LHC experiment wants to have their small scale experiment, like CMS have Mathusla, and then also.
But there's nothing, okay, which is comparable to Mathusla as far as the physics is concerned. Okay, I mean, all the other detectors, okay, I mean, they are very close by in the barrel part.
Smaller size Mathusla
Will be approved. I'm saying that probably smaller size Mathusla will be approved. Yeah, I think.
But what is the time scale? I think the time scale is more important. If you cannot approve it soon, then it will go to run 5. It will not be put into. Yeah, so that means the other experiments will be in run 4, while Mathusla will go to run 5. Any other comments, questions?
Like before that, like I am curious from both Shilpi and Swagata about, like, Swagata, you discussed about the triggers for mostly neutral long-lived particles, and Shilpi, you also talked about charged long-lived particles. So, and you one of your main triggers was, if I understood correctly, was on the MET of the particle. So, what other differences are there between the triggering on neutral and charged long-lived particles?
Triggering on charged long-lived particles is probably easier because also it depends a little bit on the lifetime. But let's say you have a charged long-lived particle produced, and it will give a very clear track in the tracker, and there is a high chance that it will be reconstructed as either an electron or a muon, or maybe even a jet, although the probability is lower. So there is a high chance that if there is a well-defined track which is reasonably high PT, it will get triggered in some fake object. For neutral long-lived particle, we have a higher chance to completely miss that.
There is just one more thing I would like to add. There are cases which I showed also in case of disappearing tracks. although it's a charged particle, but if we just consider track at HLT, that is currently not considered. So you have to trigger on jets also, jets in such cases. But yeah, just wanted to add that is something for disappearing tracks that could be a limitation. But yes, if we have dedicated algorithms, then at HLT or level 1, then we can better trigger.
I have a sort of uninformed theorist question. The question that was asked some time back about there being a succession of LLP or an LLP sector that might lead to disappearing tracks or decay gaps in succession. Now, is it easy in such cases, or how difficult is it to reconstruct the sequence of decays given the rather small time intervals? Have people thought about this? A decays to B and C, and when B is also LLP, that goes to D and E or whatever. So these successions, what is the minimum time delay or decay gap or minimum lifetime that enables one to reconstruct the sequence? Because that can contain a wealth of information. At the same time, that can, this wrong identification of the sequence may completely confound somebody. So it is just a curiosity as to whether people have thought of this kind of...
I haven't heard of discussions maybe, but about the, like in HLLHC, we will have MTD, as Shinananda was also discussing, which will have a timing resolution of 30 picoseconds. Or so if the LLP decays in there and further LLP decays in there, then that kind of
So in terms of time sequence, 30 picoseconds, and
more than if it is more than 30 picoseconds.
In terms of distances, we can roughly say 30 picoseconds times C.
Right.
Okay.
Right.
So
I think I mean, if there are any other comments to add, then this is just a...
No, of course I can understand that. But I am just thinking in terms of an LLP sector, and in analogy with the dark sector that we often talk about in dark matter analysis. Of course, cascades. Yes. Yeah, I know it is quite exotic, but since in the dark sector people are talking about such exotic situations, I am just wondering whether people have thought about it.
Just one thing, if the final particles that are being produced in this situation is, let's say, some hadronic energy deposit, then it is highly likely that it will pass the trigger threshold somehow and the event will be saved. But as far as I am aware, nobody is looking from the perspective of this kind of models. So if this kind of BSM scenario exists, we will likely miss it even though the event is there. So if you have a paper which discusses this, can you send that to? Okay.
It is something that I myself concocted, this possibility.
Okay. Just one more thing that I said, it's not simple 30 times C, because then there is some 68% chance that it could
beta factors can be
yes, I mean, there
non-trivial. But beta factors come non-trivial. I'm just saying, just to give an estimate of the length scales, I was asking the question.
So on a different note, like for these disappearing charge tracks, Shilpi, you talked about the soft pions because they have energies of around 100 MeV. That's why they cannot be picked up. So like, is there a scenario where like what is the threshold above which the soft, like they can be actually tracked?
So essentially it's not picked up because it's curling in itself. But there are now recent developments in Atlas. They have already developed some algorithm to pick up these. Of course, they come with a height. No, not timingless, but just using tracker reconstruction. They pick up the remaining hits which are left from the standard track reconstruction algorithm. So in run 3 or in next runs, this could be an important or interesting feature.
Is it something similar to what we call loopers in CMS tracking algorithm?
Yes, probably. I'll have to check.
Okay, I think we have covered the session already. So still, and it will be lunchtime now. Okay, so if still we have some discussion points, we can spend some more time and then. You have other questions? You can. No, you can make some more models right now and. Okay. Any others from the students, young people? Because this will be your search domain, LLPs, few years from now. So you can get things clarified. Okay, so if there are no other questions, I think let us thank all the speakers.